Okay, hello everyone. This video I'm going to show you the transverse shear calculation in the beam. Okay, and the transverse shear calculation, well, simply speaking, the shear stress in a beam when the beam is subject to external loading. And transverse shear, the formula for transverse shear in beam, I think in the slide I already demonstrated this. Okay, VQ over IT. So in this video, I'm not going to talk about the formula once again because we have already talked about this before. So what I'm not, right now, what I'm trying to do is going to show you how to calculate a problem or example 12.3 from a textbook. Okay, is that there is a beam here, and this is a cross section area. This is a cross section of the beam, and it give you the dimension of this cross section. And this is called Y flange. Okay, this shape is called Y flange. Is that this Y flange beam is subject to the shear 80 kilonewton, and then he want to plot the shear stress distribution along the cross section area. Actually, I want to reduce this problem a little, simplify the problem a little bit. We just, okay, all this, because the problem want to draw the distribution, but all I want you to do is calculate the shear stress at B prime, B, and C. Okay, B prime, B, and C. That's all I want to do in this problem. You don't have to draw the complete distribution because that takes too much time. Okay, so, okay, so let's look at this cross-section area again. Okay, this is the cross-section area. I want to calculate the shear stress at B prime and B and C here. Okay, and the B prime, what's the difference between B prime and B? B and B prime, they are very close to each other. The only difference is maybe I need to draw a big picture, draw a much bigger picture for B and B prime. So what's the difference between the B and B prime? Okay, so let's zoom in the B and B prime. Okay, so here, and yeah, that doesn't look very big. Okay, so okay. Okay, what's the difference between B and B prime? B prime is here and B is here. Okay, B prime is right above, a little above this dash line, and B is just right a little below the dash line. Okay, so B and B prime, they are very close to each other. Their only difference is their thickness. B prime has this thickness, and B has this thickness. Okay, thickness here is TB. I think here thickness here is TB prime. Okay, B and B prime has very close to each other. It's B prime is just right a little above the dash line. B is right a little below the dash line. Okay, the only difference is their thickness. Okay, this is related to okay, and they have the same Q. Okay, because the Q is all the same. Okay, but I'll talk about the Q later. Okay, so so let's talk about the shear stress calculation. The formula for shear stress calculation in beam is I think you should take a note on this equation. Okay, it's VQ over IT. Okay, V is the shear force, Q is the moment of area. Okay, no, not the okay, more specific, the first moment of area. Okay, we have talked about the first moment of area. Okay, and I is the moment of inertia of the cross section area, and T is the thickness of the cross section area. Okay, so and then we want to calculate the shear stress at the B prime, shear stress as B, and shear stress as C. Okay, and for such problems, for the calculation in beam, the first point, the first very important point, the first point is very important. First point, you need to determine your neutral axis. Okay, and for this this symmetry cross-section area, yeah, is the problem already tell you, yeah, here is your neutral axis, that call it NA. Here's the neutral axis. Neutral axis is right at the middle of this shape. So this problem already give you a neutral axis. You don't have to find a neutral axis again. It doesn't look at the previous example. In the previous example, you have to determine a neutral axis by yourself. But in this problem, it's already tell you, okay, the neutral axis is just here. Okay, you don't have to calculate again. Okay, so let's from the description of the problem description, what do we have? We know it's a shear force. We know, okay. The shear force we understand the shear force. We know that from the problem description, we know the shear force. V is 80 kilonewton. We already know. Okay, so we don't have to calculate or it. Okay, and the next thing is we need to know the Q, I, and T. Okay, and the next problem we should calculate the moment of inertia. Okay, a moment of inertia. Okay, moment of inertia of this cross section area, because no matter it's B prime, B or C, B prime, B or C, they are on the same. They are on the same cross section area. So have the same. They have the same. So they have the same. They have the same. They have the same. They have the same I. Okay, that's very important. Yeah, because these 3 points are on the same cross-section area. So IB prime equal to IB equal to IC. Okay, I. They are all the same. Okay, so let's call it I. Okay, so next day we have to calculate I. What's the I of this cross-section area? Okay, so moment of inertia calculation. Okay, so first of all, you need to know is this is a complicated shape. This is a complicated shape. So for the calculation, the moment of inertia of a complicated shape, you have to divide your cross section area into small. Divide your area in a complex area into a very simple piece, simple area. So we can how do we divide? We divide it by how do we divide? We divide in this way. I just make this type of division. I just cut here and I cut here, and then I call here is 1, I call here is 2, and I call the middle part is 3. Okay, I is equal to I1 plus I2 plus I3. Okay, I1 plus I2 plus I3, but actually it's symmetry. Actually, I1 is equal to I2. Okay, you should know this. Okay, because of symmetry, I1 is equal to I2. And the next problem is, okay, what is I1? Okay, so when we calculate the moment of inertia of composite area of complication shape, okay, don't forget determine its centroid of each section. Centroid is here, and the centroid is here. Okay, so let's calculate what is I1. Okay, the I1. Okay, so we look at the neutral axis right now is here, but this neutral axis does not pass through the centroid of area 1. Okay, so you have to use the parallel x theorem to calculate the moment of inertia of moment of inertia of area 1, because the neutral axis does not pass through the centroid of area 1. Okay, but at the very beginning, so you still need to calculate the moment of inertia of area 1 around its centroidal axis. So don't forget our more formula. Okay, so the neutral axis right now is horizontal. So here is your B, and here is your H. So it's it 1 over 12 B H cubic. Don't forget it. Okay, so B. Okay, so yeah, it's 0.3 meter. Okay, let me see. The dimension. What's dimension? Oh, but the problem is millimeter. Okay, so it's equal. Okay. Okay, so the B is 300 millimeter. Okay, B is your 300 millimeter. 300 millimeter. And the height is here. Height, what's it's the height? The height is 20 millimeter. 20 millimeter. And then cubic. And that's not finished. We have to plus the AD square. We have parallel x theory, AD square. So The cross section, the area of area one is times 10 to the power minus 3 is A is 20 times 10 to the power minus 3, and D is the distance between your centroid and neutral axis. Okay, so what is the D? What is the D? I call it D1. Okay, here is 100 millimeter and here is 20 millimeter. Okay, so here actually is 100 millimeter. Understand? Here is 100 millimeter and here is 220 millimeter, and it's a centroid. So you have divided two. So it's 100 and 110 millimeter here. Okay, so be careful. So this A is here, is AD square, is A and D square. Okay, what is D? 100 times 10 to the power minus 3 square. Okay, so okay, you can calculate what is I1. Okay, so after using your calculator, I don't demonstrate this anymore because I want to save some time for this problem, because this will take lots of time. Okay, so it's equal to 7.28 times 10 to the power minus 5 and 4. Okay, I1 and okay, we finish the calculation on I1. And I1 is I2. We don't have to calculate I2 again. Therefore, you have the remaining part is I3. So I will calculate I3. Okay. And I3 is very lucky. I3 is the middle part. And we see the neutral axis is passing through the centroid of the middle part. Yeah, right? The neutral axis is passing through the centroid of area 3. So you don't have to use the parallel axial theorem. You just use the formula for the rectangle directly, because the neutral axis is passing through its centroid of area 3. So here is your B. What is your B? I think the B is here. B is here, 15 millimeter. Here is your B, and here is your, right now here is your H. Your H is 200 millimeter. Okay, don't forget this one is 2B times 10 to the power minus 3 BH cubic, right? So it's 200 10 to the power minus 3 and cubic. Okay, so this I think this will also just use your calculator. Be careful using your calculator. So you will have the answer is 10 to the power minus 5. So what is I? Okay, I is equal to I1 plus I2 plus I3. Actually, it's 2 times I1 plus I3. Okay, so what's your final answer here? Okay, what's your final answer? Okay, the final answer should be 15.5610 to the power minus 5. Okay, so I is 15.5610 to the power minus 5, and its unit is M4. Okay, okay, that's the moment of inertia of this cross-section area. Okay, so let's finish another important, but the calculation we haven't finished, because we'll also calculate Q. Okay, the first moment of area. Okay, the first moment area. Yeah, be careful, because B and B prime and C, these 3 points have different Q. So you have to calculate QC prime, QB prime, QB prime, QB, and QC. Yeah, we haven't finished. Okay, so for I need more space, so I have to erase some parts of this screen. So if you want to review, just please rewind it. Okay. Okay, so okay, first of all, let's calculate the QB prime and QC. Okay, and QB prime and QC, in this problem, QB prime is equal to QC. This a little, maybe a little explanation. Yeah, yeah, we have to calculate so-called QB. Okay, so let's calculate. Okay, we calculate QB prime first. Okay. Okay, QB prime is just the first moment of area. It's just area times the distance between centroid. Uh, and it's area times the distance, and the distance is the between the neutral axis and the centroid of area. That's it. Okay, so and then there is some rule. Okay, we have talked about this in the previous slide. If you okay, so this is our neutral axis. Okay, this is our neutral axis here. Or maybe I will erase here some here. Okay, okay, okay. So yeah, right now no matter it's b prime or to b, it's above the neutral axis. So when it comes to calculate qb or qp prime, just calculate it's above b and b prime. Okay, understands? Right now, B and B prime is above the neutral axis. So when it comes to calculate QB or QB prime, it's calculated above area, above the B and B prime. Because right now, B and B prime is above neutral axis, above neutral axis. So the QB and QB prime is calculated QB and QB prime could be above B and B prime. So that means you calculate the area here. That's the QB. That's the QB prime. Okay. Yeah, because right now B and B prime is above neutral axis. So you calculate the Q bit above B and B prime. Okay. And the problem is that's I just mentioned in the very beginning of this problem. B and B prime are very close to each other. So actually, B and B prime is the same in this problem because B and B prime are very close to each other. B prime just above the dash line, B just a little below the dash line. So we cannot tell because this is so small difference. So we just assume okay, B and B prime share the same Q. Okay, the only difference B and B prime is their thickness. Okay, I'll talk about this later. Okay, so actually Q and QB prime is the same. Okay, and what is Q? It's just the area times the distance between the neutral axis and the centroid of area. So where right now we can only consider the area. This is right now the area we consider right now. This purple slash. Okay, the purple slash here. This is the area we only consider right now. So okay, so what's our area? The area is, I think the dimension of area is 20 millimeter times 300 millimeter. 20 millimeter times 300 millimeter. That's our area. Okay, I want to consider just the A1. Okay, this is A1. 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 Okay. Okay, okay. And also, so what's the distance between the centroid of area 1 and neutral axis? We just calculated before 110 millimeter, right? Let me check. Do I calculate right? Yeah, 100 millimeter, 100 millimeter. Okay, so that's the QB and QB prime. Okay, so what's the answer? Yeah, I just don't waste too much time. So it's just the calculate by yourself. It's equal to 6.6 times 10 to the power minus 4. I think the unit is area times the distance. So I think the unit is m to the power 3. Okay, so that's QB and QB prime. Okay, but don't forget we still have to compute the shear stress at C. So we have to calculate the QC. Okay, so we have to calculate QC. Okay, okay, so I can leave this here. Okay, so QC, what is QC? Okay, so right now QC, yeah, we can say QC is very close to neutral axis. So it's also right now QC, we just calculated everything above C, everything above C, everything above C. So we have two area. Okay, we have this area. Okay, maybe I should try to draw this again. I should try to draw this again. Right now our neutral axis is here and C is here. So we just compute everything above C. We calculate everything above C. Okay, and the C here we can divide the C into these two shape. This is their centroid. Okay, I call it I call this is 4. This is 1. Okay, so what's about QC? So you need to calculate A4 times Y4 times and plus A1 times Y1. Okay, let's start with this one first because we already calculate what's the area of what area one. Oh, yeah, we just calculate 20 times 10 to the power minus 3, 300 times 10 to the power minus 3. And this is A1. So what's Y1? What's the distance between this neutral axis and centroid of area 1 is 110 millimeter, right? 110 millimeter. 110 millimeter. Okay, so this is the first part, but we have this part. Don't forget, we have this part because we have to calculate everything above C. Everything above C. We just finished this part calculation. We have this part calculation. Okay, what is this area? Okay, this is 50 millimeter, right? And this here is 100 millimeter, right? Yeah, go check your dimension of the figure. So it's plus, yeah, 15 times 10 to the power minus 3 millimeter times and this 100 10 to the power minus 3 millimeter and times your distance between the centroid of the new and the neutral axis. So what is the distance here? Okay, so I think here is this is 100, so I think this is 50 millimeter, right? 50 millimeter. So okay, so this is 50 millimeter. Okay, and then you add these two together. That's your QC. Okay, okay. So okay, once again, just check your using your calculator properly and practice it. So the QC will be 7.35 times 10 to the power minus 4. I think is m cubic unit m cubic. Okay, and okay, so we solved the I out and solved the Q out. The remaining part is what's our T? T is the thickness of the cross section area. Okay, so T is very simple. So I just what I just said. TB is equal to 300 millimeter. TB is 50 millimeter. And what is TC? TC is also 15 millimeter. It's based on the geometry information of this problem. So we have everything. So we can calculate the shear stress at B prime, B, and C. Okay, just put everything in the formula. Okay, so do I have any space here? Let me see. Do I have any space? Okay. Let me see. Okay, so I need some space. So maybe I just erase some parts of this problem. So QB, we already know it. Okay, so if you want to see this, please rewind. And we also know the QC. We just compute the QC. Yeah, it's not easy, right? QC is 7.35 10 to the power minus 4 and cubic. Okay, so I erase this part. Okay, so finally, we finally can calculate the answers. Okay, that's why shear stress calculation indeed takes very, very long time. You have lots of things to calculate. So also is our B prime. So V is the same 80 kilometer Newton. Okay, and what is QB prime is here 6.6 times 10 to the power minus 4. Okay. So what our in moment inertia is 15.56 times 10 to the power minus 5. And finally, the P, what is TB? Yeah, TB prime, 300 millimeter. Yeah, that's all. So what's your answer? Yeah, calculate by yourselves. 1.131 mega pa. Okay, right? So what's our shear stress at B? The shear force the same. And the QB is equal to QB prime. So, okay, a moment of inertia is on the same cross-section area. Moment of inertia on these 3 points are all the same. The only difference between B and B prime is thickness. It's TB is only 15 millimeter. Okay, because it has thin thickness, so that's why it takes a lot of stress. So if you put into a calculator, you will get the answer. Yeah, I think I don't want to demonstrate the detail of this calculator stuff. Okay, so it will become 22.62 megapart. Yeah, because you have small cross section area on this B here, so yeah, take lots more stress. Okay. Okay, so the final one is C. Okay, C. Shear force the same. What is Q at C? QC here. 7.35 times 10 to the power minus 4. Moment of inertia, same. And the cross section area, yeah, sorry, not cross section area, thickness, minus 3. Okay, so after you put in the calculator, it will be 25.19 mega. Okay, that's the answer. That's the answer you will see on textbook. Okay, so here is the shear stress calculation. Shear stress calculation in beam when it's subject to a external loading. Yeah, it's not very easy because you have to calculate moment of inertia and first moment of area simultaneously. Okay, and sometimes you also have to calculate moment of inertia, and sometimes you calculate moment of inertia and calculate moment of first area. You have some in this problem. We are dealing with a composite area or complicate area. So you have to divide your system into your simple area, okay, and then calculate moment of inertia and Q and first moment of area. And the moment of inertia, you also have to consider the parallel X theorem sometimes. Okay, so it takes lots of effort to calculate the shear stress in beam. Okay, so that's why you need to get used to this. Yes, there's no simple way to do this calculation. I think this is the most simple way to do the calculation. Okay, so I just start video here. See you in our video. Bye bye.